Hello again to all those interested in implementing a multi-agent artificial intelligence system in a wind farm. This video is specifically aimed at technical directors, operations and maintenance managers, digitalization leaders, CTOs, innovation managers, and plant managers. The goal is to bridge the gap between the theoretical design of advanced systems and their practical deployment in real-world operating environments. We'll cover each critical phase, from initial conceptualization to ongoing consolidation and optimization. You'll understand how to transform theory into a tangible and sustainable operational advantage. This video is essential for establishing a roadmap for successful implementation. The implementation of any advanced technology, such as a multi-agent system, presents a fundamental contrast between its theoretical design and its practical application. On paper, artificial intelligence systems promise revolutionary efficiencies and unprecedented optimization. However, operational reality demands a structured methodology to avoid common pitfalls. Without a clear plan, the promise of AI can become a source of frustration and unexpected costs. One of the most common problems is data chaos, with unclassified signals preventing consistent interpretation. This leads to significant technical resistance, often due to poor communication about the system's benefits and operation. Another challenge is the disconnect between existing systems such as SCADA, CMMS, and the new AI layer. This lack of integration creates information silos and reduces overall effectiveness. Early errors, no matter how small, can quickly erode the operating team's confidence in the new technology. A structured implementation is vital to maximizing the benefits of artificial intelligence. It minimizes deployment risks, ensuring a smooth transition and successful adoption. It is the foundation for building a robust and reliable system that generates real value. The first phase, initial diagnostics and modeling, is crucial to laying the foundation for the multi-agent system. Its main objectives are to understand existing data and identify any information gaps. This involves mapping all key signals from SCADA, condition monitoring systems, CMS, PLCs, and maintenance management systems, CMMS. It is essential to identify the specific characteristics of the wind farm, such as its topography, turbine type, and environmental conditions. With this information, the logical model of the agents is built, defining their roles and expected interactions. This initial modeling is a conceptual but highly technical step. The results of this phase include a detailed map of all available sensors and data systems. Blind spots, or areas where information is insufficient or non-existent, are also identified. From this, precise recommendations are generated for the inclusion of complementary sensors, such as IoT devices, vibration sensors, or audio systems. This phase ensures that the multi-agent system is built on a solid and comprehensive database. It allows for a deep understanding of the operating environment before any development or integration. This is the stage where the data architecture that will fuel the artificial intelligence is defined. The second phase focuses on capturing implicit knowledge, an often underestimated but invaluable component. The main objective is to incorporate undocumented knowledge that resides in the experience of field technicians. This knowledge includes recurring patterns and issues that are not typically recorded in formal systems. The methodologies for this capture are diverse and advanced. Techniques are used to record and transcribe the technician's perceptions and know-how. Here, a specific subagent, Subagent 6.1, comes into play, tasked with the structured collection of these narratives. Natural language processing, or NLP, is then applied through Subagent 6.2 to structure the voice and text data. This allows relevant information to be extracted and transformed into a format usable by the system. This implicit knowledge is then connected to historical data and existing technical records. The integration of this practical knowledge significantly enriches the knowledge base of the multi-agent system. It allows artificial intelligence to understand nuances and exceptions that purely numerical data cannot reveal. This phase is key to building a system that is not only intelligent, but also contextual and pragmatic. The third phase is the installation and connection of the agents, where the multi-agent system begins to take operational form. The main objectives are to set guidelines for the virtual agents and connect them to real-time data sources. This involves deep integration with the existing infrastructure, whether at the edge or in the cloud. At this stage, several key agents are activated. A control agent is deployed for each wind turbine, responsible for management and optimization at the individual level. A data and communications agent handles information flow, ensuring connectivity and data integrity. A cybersecurity subagent, 5.3, is activated to protect all communications and system access. This component is vital to ensuring the resilience and security of the infrastructure. Rigorous technical validations are performed at this stage. Latency times are checked to ensure a rapid system response. Data integrity is meticulously verified to avoid errors. Finally, secure two-way communication between all components and agents is established and validated. The fourth phase is the implementation of a pilot in a controlled environment, a critical step to validate the system before its full-scale deployment. The main objective is to test the system on a reduced scale, allowing for a detailed evaluation of its performance. Predictions, generated alarms, and suggestions provided by agents are validated. This phase allows for fine-tuning the models and decision flows in a realistic but limited environment. Typically, the scope of a pilot includes 3 to 5 wind turbines. The testing period is typically 4 to 6 weeks, providing sufficient time to observe the system's behavior under various conditions. The direct involvement of maintenance technicians is crucial in this phase. Their feedback is invaluable for fine-tuning the system and ensuring its usability. Several key performance indicators, or KPIs, are monitored to assess the pilot's success. The accuracy of the system's predictions and the acceptance of recommendations by technicians are measured. Reducing false positives is a critical KPI, as it minimizes unnecessary alerts. Finally, the operational value added by the system's decisions is quantified, demonstrating their real impact. The fifth phase, explainability and human validation, is essential to building trust and ensuring system adoption. The main objective is to ensure that the system's recommendations are understandable to end users. This involves training technicians and supervisors in interpreting models and their outputs. It is essential to avoid the black box syndrome, where AI decisions are opaque and inexplicable. To achieve this, specific subagents are involved. The Prediction Explanation Generator, Subagent 7.1, translates complex AI decisions into clear and accessible language. The Technical Report Converter, Subagent 7.2, transforms raw data into structured, easy-to-understand reports. Active strategies are implemented to build trust in the system. AI decisions are compared with historical decisions made by humans, demonstrating their consistency and improvement. The economic impact of each decision suggested by the system is shown, quantifying the value generated. Before scaling, all critical recommendations are validated by team leaders. This phase ensures that the system is not only intelligent, but also transparent and reliable for operating personnel. The sixth phase focuses on scaling and continuous optimization, bringing the multi-agent system to its full operational capacity. The main objective is to scale the system to the entire wind farm, extending its benefits to all turbines. Global optimization agents, such as those that manage the wake effect, are activated to maximize the farm's energy production. Continuous retraining mechanisms are implemented for the artificial intelligence models. This ensures that the system adapts to new conditions and learns from the latest data. Several key actions and agents come into play in this phase. The orchestrator agent, Agent 1, is activated, coordinating all operations at the fleet level. The overall fleet optimization, led by Subagent 1.1, seeks maximum collective efficiency. The continuous learning agent, Agent 8, is responsible for constantly updating and improving the models. Finally, maintenance strategy simulations are conducted using Subagent 4.3 to evaluate the impact of different approaches. This phase transforms the system from a pilot to a comprehensive and dynamic solution capable of evolving over time. The seventh and final phase is the consolidation and governance of the system, ensuring its long-term sustainability and improvement. The main objectives are to establish continuous improvement cycles for the multi-agent system. Data, model, and access governance are formalized, ensuring information integrity and security. Executive dashboards and periodic reports are created to monitor performance and value generated. These elements are critical in this phase. A technical governance committee, composed of experts from different areas, is established to oversee the system's evolution. A panel of strategic metrics is defined, including return on investment, ROI, fleet availability, and events avoided thanks to system intervention. Rigorous version control is implemented for AI models, along with periodic validation processes. This phase ensures that the multi-agent system is not a static solution, but a living architecture that continuously adapts and improves. Proper governance is key to maintaining the system's relevance and value over time. In this video, we've outlined the 7 critical phases for the successful implementation of a multi-agent system in a wind farm. The key is to understand that a successful pilot is the foundation for building trust and demonstrating the true value of artificial intelligence. Proper integration ensures operational efficiency and maximizes benefits. A useful and well-implemented AI system quickly becomes an indispensable tool for wind farm management. Multi-agent architecture is a living system designed to evolve and adapt to the changing needs of the operating environment. In our next video, we'll explore the system's functionality from a control room perspective. We'll analyze the flow of information and how operational decisions are made. Thank you for joining us for this deep dive into the implementation of AI in wind energy, and don't forget to subscribe to the channel.